Thanks so much, Justin. I appreciate it. I'm happy to be here. So this work is, perhaps unsurprisingly, very collaborative, and the collaborators are too numerous to list, but you'll see me reference a few papers that are either published or about to be published. So I encourage you to go look at those to see the other collaborators that were involved. So jumping right in, I know that the EarthScope group includes a lot of people that aren't necessarily doing earthquake seismology. So for those of you in the room that may not be focused on earthquakes, I want to give you an overview of what we do at the USGS after a major earthquake. So if you go to the website earthquake.usgs.gov after an earthquake, you will find a link to that earthquakes event page. And this is an example from the recent magnitude 7.8 event in Turkey. And each one of these tiles that you see represents a different product that's put out by our team at the National Earthquake Information Center in Golden. And it gives information about the earthquake, either its location, its magnitude, its mechanism, the impact, things like that. And I can actually divide these into categories for the different products. So here we have two that put the event into their seismotectonic context. Where are they in relation to faults or other earthquakes that have occurred in the past? Then we have a few products that deal with the earthquake shaking. So there's a citizen science report called Did You Feel It?, where you can respond and let us know what your experience was like during the earthquake, and we can use that to help constrain where shaking occurred. And then this shake map shows the estimated intensity of shaking using either ground motion scaling laws, instrument recordings, or those responses from Did You Feel It? We also have a couple products that deal with the earthquake's impact. So on the left, this is Pager. It's basically a loss estimation. So we estimate both the economic loss and the estimated fatalities from an earthquake on a color scale from green, yellow, orange, and red. And then the ground failure product, which provides an estimate of the probability of landslides and liquefaction in the area due to the earthquake shaking. And then finally, these three on the right give information about the earthquake source itself. So things like the origin time, the location, the mechanism of the earthquake, is it strike slip, reverse, or normal faulting? And then finally, the finite fault model, which is what I'm going to be focusing on during this talk. So the finite fault model is basically a rapid estimate of the location, timing, and amount of motion that occurs on the fault. It's also known as a slip model, and basically it helps to clarify that an earthquake doesn't happen at a single point in space and time. Moderate to large earthquakes can rupture over large distances, and they can rupture for many tens of seconds to even a few minutes for the largest earthquakes. And so why does this slip distribution matter? So here's an example from two earthquakes in 2021 in Qinghai, China. And here are the shake maps from those two earthquakes. So on the left, there's a magnitude 5 earthquake, and you can see that in this case, warm colors represent higher intensity shaking. So for the magnitude 5.5 earthquake, you have the highest intensity shaking around the epicenter, and then sort of decaying more or less evenly in all directions as you move away from the epicenter. But for this magnitude 7.3 earthquake on the right, we have a very different pattern where you have shaking that is most intense, not only at the epicenter, but in this elongate east to west pattern that extends in both directions from the epicenter. And basically that follows the fault length of this earthquake. So in short, shaking is related to the distance from the fault rather than distance from the initiation point of rupture, the hypocenter. And because large earthquakes occur over a finite area of a fault that can be tens to even hundreds of kilometers in length. For these larger earthquakes, a point source becomes insufficient for estimating qualities like the intensity of shaking. So knowing the slip distribution, or at a minimum, the dimensions of the slip, is critical for these shaking predictions, and then ultimately for loss estimates and damage estimates, and even for tsunami generation estimates. So in this slide on the top left, you're seeing the slip pattern that I estimated for this magnitude 7.3 event. The hypocenter here is denoted by the white star. And you can see that the largest slip asperities occur on both sides of the hypocenter, indicating bilateral rupture, and it extends in both directions for tens of kilometers. And that's why we get this elongate shaking pattern. So very briefly, how do we solve for this slip pattern? How do you create a finite fault model? So first off, modeling requires that you assume the fault plane orientation. So basically a strike, a dip, and an average rake. And we generally take this from the rapidly estimated moment tensor, which obviously gives you two potential planes, and we use either data fits or knowledge about the tectonics of the region to choose the more likely plane. Sometimes if it's in a confusing area and we don't know, we'll publish both. We create a rectangular fault plane from that strike and dip, and divide it into smaller rectangular boxes like you see on the right here, called subfaults. This is just an example for the magnitude 8.2 earthquake in Alaska a couple of years back. For context, and you'll see this a bunch later in the talk, this red line indicates the up dip edge of the fault. So when you look at these maps, you have to kind of imagine the plane dipping down underneath the Aleutian Peninsula to the north. And so basically, we invert the available data to find the timing and amount of slip on each of these subfaults that best fits whatever data is accessible to us. We also, and you'll see this later in some of the examples, can create multi-segment models that have fault segments with varying strikes and dips for more complicated earthquakes. So once we've solved for the amount and timing of slip on each of these individual subfaults, these little boxes on the right, we can sum them up, and that total slip and timing gives us the earthquake source time function, or the moment released with time. So that's what you're seeing here on the left. In this case, it hit a peak moment rate at about 25 seconds after origin time, and then decayed more or less evenly. And these red lines indicate where we assume the end of rupture to be, because when you run a finite fault model, there's always some amount of slip at the end of the rupture that's really just fitting waveform noise. So just some history on finite fault models at the USGS. Since late 2007, USGS has been publishing rapid finite fault models using teleseismic data. So most notably, these are available in a 2017 publication by Gavin Hayes that detailed the rupture properties inferred from these rapid models, as well as some retrospective analysis of earthquakes going back to 1990 using the same method. So teleseismic data is ideal for this purpose because it's available for a global earthquake distribution. So it doesn't matter if we have a local data set or not. And this bottom figure here shows the broadband stations across the globe that are feeding into the National Earthquake Information Center's 24/7 earthquake response. So we can get data from earthquakes anywhere in the world and use it to create these models. It's also pretty simple to calculate Green's functions at teleseismic distances because they don't require us to have any detailed knowledge of the seismic velocity profile at the earthquake's location. So that's a nice, simple thing that we don't have to worry about in rapid response. But because teleseismic data has to travel through the globe, and we have obviously seismic attenuation as it travels. Relying on teleseismic data limits our ability to resolve earthquakes smaller than magnitude 7. So basically, we only have been putting out these models for earthquakes bigger than magnitude 7 because of that reason. And second, it in part limits the timeliness of our rapid models because of seismic propagation speeds. So we can start these finite fault calculations after a few tens of minutes, but in order to see full wave propagation at teleseismic distances up to 90 degrees, we have to wait about 50 minutes after origin time to have the full waveforms. So that's another limitation of using teleseismic data. So some things that we are doing to reduce those limitations is that over the last 2 years, we've undertaken efforts to expand the National Earthquake Information Center's capability to include local observations as well. So we have strong motion accelerometer data, interferometric synthetic aperture or radar or INSAR data, and global navigation satellite systems or GNSS data. So in a perfect world, we can get some of these local data sets, namely the strong motion accelerometer and GNSS, in real time faster than we can get teleseismic data, because of course they'll observe the full propagation of the seismic waves faster when they're local stations. INSAR, of course, can take hours to days to be included depending on when the next post-earthquake image is taken. So for the rest of this talk, I'm going to focus on 3 examples where the addition of local data has been useful in the last couple of years. So first, I'll talk about the 2021 magnitude 7.2 earthquake in Haiti. And for more details, this work has been published in a paper in SRL last year. Next, we have the magnitude 6.2 earthquake sequence in Petrolia, California from 2021, not to be confused with the one the same date a year later. This has been recently published in Nature Communications and work led by my colleague, Will Yeck. And finally, I'll show some more recent results about the Marash earthquakes in Turkey, which has just been accepted at the seismic record and should be available in the next couple of weeks. And so quick thanks to all of the co-authors of those papers, and please check them out if you want some more information. So starting with the 2021 magnitude 7.2 earthquake in Haiti, it's been a while, so I'll give you some quick background. So it occurred on August 14th, 2021, about 150 kilometers west of Port-au-Prince, and resulted in thousands of deaths and injuries and hundreds of thousands of damaged structures, with economic loss totaling over $1 billion US. If you're not an earthquake seismologist, keep in mind that a magnitude 7.2 earthquake is nearly 2 times stronger in energy release than the magnitude 7.0 earthquake from 2010, but of course this occurred in a much less densely populated area than the one in 2010, which is perhaps why it didn't receive the same sort of coverage. And particularly frustratingly for seismologists like me who were trying to rapidly characterize this earthquake for purposes of rapid response, it occurred roughly half an hour after a magnitude 6.9 earthquake in Alaska. And that might not immediately seem important, but when you're working with teleseismic waves that make their way all around the globe before being incorporated into your modeling procedures, an earthquake that occurs far away but close in time can be a big hindrance to those modeling efforts, because the seismic waves from the earlier event will be sort of included in the data that you're trying to use for your modeling purposes. And so that did end up being a problem when I went to model this earthquake. I'll explain to you the model, but first I'll just get you oriented. So here's Haiti on the left of your screen and the Dominican Republic on the right side. And this thick black line shows the fault trace of the Enriquillo Plantain Garden Fault Zone, which is a known structure that we think this earthquake occurred either on or near to. And this black outlined area is our inferred fault plane with the red line indicating the up dip edge. So again, you have to imagine the fault dipping into the screen to the north. And the colors on each of these subfaults indicate our modeled slip distribution. And if you sum the timing and the amount of slip on each of these subfaults, you get this moment rate function on the right. So which indicates that peak moment rate occurred prior to 10 seconds, and then the event was over in about 20 seconds. So looking at this slip distribution, you'll notice that the main slip asperity is just west of the hypocenter, but slip occurs in both directions, indicating bilateral rupture. And we knew early on that this model would not be reliable. We had interference from that earlier magnitude 6.9 Alaska earthquake merged with the teleseismic signal from the Haiti earthquake. So many stations recordings were just not usable, and we ended up with a pretty small set of observations that were going into this inversion. So soon after I posted this model to the event pages, we started noticing that early aftershocks were happening almost exclusively to the west of the hypocenter, suggesting that rupture was likely also unilateral to the west rather than bilateral, as this model suggests. So over the next few days, we were able to get additional data from local networks that helped us to clarify the slip distribution. So here's an updated model showing what the slip distribution looks like when we add in observations from a single strong motion accelerometer station here and 5 static GNSS stations in the Dominican Republic. These were estimated by formerly UNAVCO. So in the top right, you'll see the data in black, and the model fits in red for this strong motion accelerometer station. And on the map, the black arrows indicate the observed GNSS offsets estimated by UNAVCO and the model predictions in red. And these offsets might not look very good, but keep in mind just how incredibly small this scale is that we're looking at. And remember that GNSS has relatively large errors in comparison to seismic data sets. So you may have already noticed before I pointed it out that our slip model has changed dramatically. Adding just this small amount of data, the single accelerometer station and 5 static GNSS sites have changed the understanding of the earthquake rupture. So now we just see a major slip asperity directly to the west, smaller slip asperity even further west, with no notable slip in the east direction, which confirms our suspicion of unilateral rupture that we were unable to resolve with the poor quality teleseismic data. And then days later, we were able to access INSAR observations from the Sentinel-1 satellite. We included an ascending and descending track, just one of which I'm showing here on the right. So you have the observed line of sight displacements in the top left, our model synthetic fits in the top right, our misfit in the bottom left, and a long period ramp signal in the bottom right that we estimate simultaneously with our slip estimate to separate it from the true earthquake deformation signal. So now including all of these observations, so we have the few teleseismic waveforms that we were able to salvage, 1 accelerometer station, 5 static GNSS sites, and 2 interferograms. We have our final model here, which is composed of 1 sort of elongate slip asperity starting at the hypocenter location and rupturing unilaterally to the west, with a few other small slip patches of perhaps lesser importance. So moving on to our next example, this is the December 2021 Petrolia Sequence in Northern California. This earthquake occurred near the Mendocino Triple Junction, which is a region that connects the San Andreas Fault to the south to the Cascadia subduction zone to the north. And originally, when this data came in, we interpreted it as a single magnitude 6.2 earthquake. But soon after, we identified two sources of P waves, one that was offshore and one that was onshore, and they were separated in time by about 11 seconds. So due to that spatiotemporal proximity, the observations that we have include the combined signal of that offshore and onshore rupture. And because the earthquakes were in the low magnitude 6 range, that's too small to be reliably characterized by teleseismic data alone. But lucky for us, because this occurred in Northern California, it was observed by a very dense seismic and GNSS network. So in this map on the left, the inverted white triangles are the locations of strong motion accelerometer stations, and the black arrows represent GNSS static offsets. We assumed the locations of so we have the locations, the hypocenter locations of the two ruptures. We assumed the offshore fault to map along the transform boundary here, and we used aftershock relocations to estimate the orientation of this onshore rupture. And so using the available teleseismic data that we have, so we have some teleseismic data to help us constrain the timing, although those don't have great resolving power for smaller magnitude earthquakes. We have all of this strong motion data and static GNSS data. We're able to invert these two ruptures, offshore and onshore, simultaneously to estimate the slip on both features. And sorry, I did not put these up, I just talked. I'll jump right to the result of that joint inversion. So now on the map, you're seeing red arrows that indicate the model fits to the GNSS static offsets. And on the top right, this is the slip pattern modeled for the offshore fault, and underneath the slip pattern for the onshore fault. So in both of these, the stars represent the initiation point of rupture. And you'll see rupture contours drawn every 2 seconds, demonstrating how rupture spread along the fault. And for this onshore fault, keep in mind that it was delayed 11 seconds. So the first contour that you're seeing is the 12-second contour. I also want to point out the directional indicators on each of these. In both, the positive along strike direction is shown toward the right. So for this offshore fault specifically, that translates to the west direction. So when you're looking at this face on, you have to imagine it flipped opposite to get your map view. So this secondary slip disparity is actually in the east side, kind of close to the shoreline here. And then in the bottom right, we have the moment rate function for these two ruptures. The combined moment rate function is shown in this thick black line. And then in pink, we have the moment rate function for the offshore rupture. And in purple, the moment rate function for the onshore rupture that starts 11 seconds later. And here I've just added to the map the contributions of the individual rupture planes to the overall static offsets. So following the same color convention that you see in the source time functions, pink arrows now on this map indicate offset contributed by the offshore rupture, and purple arrows indicate slip contributed by rupture from the onshore fault. And then as before, red is just the sum of those two. So what's particularly interesting about this inversion result is that it highlights the complexity of this sequence by showing A, how the ruptures overlap in time. So this initial offshore rupture was kind of had a lower overall moment rate and a longer duration compared to this more impulsive onshore rupture in purple. And so it raises an interesting question of whether this is two different earthquakes that are somehow triggered, or if this is just a complex multi-fault rupture. We often sort of recognize these complexities in large magnitude earthquakes involving multiple faults and variable rupture speeds, rupture durations, things like that. But we don't as frequently recognize that level of complexity in smaller magnitude events. And certainly in this case, if we hadn't had access to this dense network of strong motion and GNSS observations, we wouldn't have been able to resolve this similar level of complexity for this moderate magnitude earthquake. So it's of course my hope that the expansion of our finite fault capabilities at the NEIC will allow us to better respond to future earthquakes of interest, including moderate magnitude events like this one, because we know that moderate magnitude events can also cause significant damage if they're located in the wrong spot. So next I want to transition into some more recent work that we've done with the devastating Maraş earthquakes in Turkey just a couple months ago. This one is probably still fresh in everyone's minds, but I'll go over some key points of the earthquake just before we get into the data and modeling. So Turkey is located mainly on the Anatolian block you see here, which is part of the larger Eurasian plate. And the regional tectonics in this area are dominated by interactions between the Eurasian, the African, and the Arabian plates, which meet at a triple junction right here, just east of where this earthquake sequence occurred. So the sequence main shock, located down here, was a magnitude 7.8 earthquake that occurred around 4 a.m. local time, and about 9 hours later was succeeded by a magnitude 7.5 earthquake located to the north on a separate fault. So the main shock ruptured mostly along the East Anatolian fault, which is the main plate boundary here. And the magnitude 7.5 appears to have ruptured the Chardak fault. I hope I'm saying that correctly. And so from the focal mechanisms for each of these events that you see estimated here, these are the W phase centroid moment tensors estimated by National Earthquake Information Center. We use those to infer the orientation for our initial finite fault models, which has significant non-double couple percentage in this case. And so we sort of knew going in that a planar fault might be insufficient for modeling these, but unfortunately, early on in earthquake response, that's sort of all we have to go on. So I want to show how our modeling evolved over time during this earthquake sequence to sort of improve our understanding of these earthquakes as we had access to more local data, and what local data means at this point will be sort of expanded. So I'm also going to deviate from talking just about finite fault modeling and give a little insight into the full scope of rapid event response for these earthquakes. And so I'm going to bring in some of the other products that I mentioned earlier on the earthquake event pages, just to demonstrate how all of our products interact and get updated as new information becomes available. And you can see sort of the benefit of having these updates to our finite fault modeling capabilities. So the timeline first will show, this is origin time over here on the left. It'll show the first 4 hours, and then we'll cut to how products evolved in the days after the earthquake, starting now with the magnitude 7.8 main shock. So the first thing that comes out when we do an earthquake response is an estimate of the scalar magnitude of this earthquake that came out pretty quickly. And from that, we have an initial estimate of the shaking in the region based on the hypocenter location and that magnitude, and understanding of the geology in that region. We also then come up with our initial loss estimate, and then we also came up with our first and final estimate of the W-phase centroid moment tensor, which, as you'll recall, is how we get information to use in the as the starting orientation for our first finite fault model. A little bit after 2 hours after origin time, we posted our first finite fault model using just teleseismic observations. We didn't have access to any local observations in real time, so this is all we had to use. And then I'll show you quickly the map view here. So in our initial finite fault models, they are always tied to the hypocenter location and use the orientation from the finite fault estimate. So you'll see, even though we have the main through-going tectonic boundary here, this is the hypocenter south of that main boundary. So that is where our planar finite fault estimate is tied. And in this case, the red line indicating the up-dip edge isn't very informative because this is a steeply dipping fault, so you can't actually see the rupture pattern here. You can only see it in this figure here. And then I just wanted to show quickly how some teleseismic, this is a subset of the teleseismic body waves, observations in black and model fits in red. And then on top here, some teleseismic surface waves, again, observations in black and model fits in red. So once we have this initial estimate of the slip pattern, that then gets fed back into shake map. So now you can see that we have this more elongate pattern, like what you saw with those earthquakes in China that I showed at the beginning of the talk. So we've extended where high shaking is expected. And then that also in turn is used to update our loss estimate again. We knew that this first estimate of the finite fault model might not be great, because of the non-double couple percentage that we were seeing in the focal mechanism, this moment tensor, which suggests there might be more than one fault orientation involved. And so we were sort of itching to update that once we had more information. And in the first day afterward, we were able to get information about strong earthquake shaking to the southwest of where our fault rupture was. So we put out an updated model that had two fault segments and tried to sort of track where we were seeing these higher intensity observations. So you can see our attempt here. We're still pinned to the USGS hypocenter. So we have one long fault, and then we were seeing high estimates of shaking intensity reported in this area. So we assumed that the fault must likely go in that region too. And you can see now we're getting slight improvements to our teleseismic body wave fits, and our surface waves still look great. In the next day or so, we finally got access to a large data set of accelerometer stations, which then were used to update shake map further. So now we have this sort of two-pronged fault orientation that raises the level of shaking along the fault trace. On day 3, we had our first radar images from the ALOS-2 satellite, which helped us start to map where the rupture was. And it's at this point that we start to know for certain that the rupture actually is on this main through-going boundary and not lower where or further south where the hypocenter is, and the hypocenter is actually not on the main major ruptured fault for this earthquake. About 4 days later, we can map from Sentinel-1 INSAR imagery. So now you can see that these the stark difference in color represents where rupture is occurring. So this is related to the main shock. This is related to the aftershock, but we're not talking about that here. So we end up now using that full rupture orientation to update shake map. and then, of course, used as input to Pager. So once we had information about this rupture trace, we now know that the hypocenter is actually on sort of an offshoot of the main rupture, and we end up using two other fault segments to track where we are seeing the rupture from the INSAR interferograms. So this is a model that doesn't actually use the INSAR directly, but uses information from INSAR to estimate the rupture orientation. And on that, we're using our teleseismic data to model the rupture. And you can see, once again, these are the same teleseismic body and surface wave stations. There are many more. I'm just showing you a subset here. And every time we get a little closer and include more complexity, of course, we're getting slightly better fits to those waveforms. So this model was available about a week after the earthquake occurred. And then finally on day 10, so about a week and a half after the earthquake occurred, we had access to a set of accelerometer and GNSS stations to modify this model. So we're using the same fault orientations, but now you can see that we have data coming in from accelerometer stations in white, high rate GNSS stations in dark blue, and then all of these arrows are static GNSS offsets from stations in the area. And now, instead of showing you teleseismic fits, I'm showing you here on the top, this is a high rate GNSS waveform fit. So data is in black and model fits are in red. And then on the bottom here is one of the strong motion stations with, again, data in black and model fits in red. Just taking this away so you can see the difference here between these two versions of the finite fault model. Version 3, which included the fault trace from our rupture mapping, but was still a teleseismic data only model. And then version 4, which is modeled on the exact same fault segments, but includes local seismic and geodetic observations. So it's a little bit, I know the text is a little small, so you'll just have to believe me that that maximum slip went up slightly when we added the local data. That's not particularly surprising. Teleseismic data is not as sensitive to small scale differences, so slip kind of gets smoothed out a little bit. And slip also got a little shallower when we added the local data, which is another thing that we see over and over when we add normally local geodetic data, so GNSS and INSAR mostly. So now, in the interest of time, I'm not going to go through the second event as slowly, but now you'll see on the bottom half of the screen, we're using the same timeline, but now related to the origin time of the magnitude 7.5 earthquake to the north. And a couple interesting things to point out is the slight delay that we had in these first products coming out for this aftershock relative to how quickly they came out for the main shock. So remember, we're relating this timeline to the origin times of each event. So for example, you can see that the moment tensor came out slightly later for the magnitude 7.5 event than we got it out for the main shock. And that's sort of because of this same teleseismic data issue that we were having in Haiti. When you have a very big event that occurred earlier, those waves are still bouncing around the Earth, so it's hard to get sort of a stable solution that you know only includes source information from the earthquake you're trying to model. But other than that, we had some sort of similarity across the timeline for when products got updated. We had our first single plane teleseismic observation finite fault model that came out a little after 2 hours after origin time. And there was a second version in here that I didn't bother showing, but finally toward the end, on day 10 after rupture, after the earthquake occurred, when we have information from the INSAR data to show that we have this sort of 3-segment rupture, we modeled slip along those 3 segments and ended up with a slip pattern that has a much higher maximum slip, or sorry, higher maximum slip than the main shock, because it's an earthquake that's more kind of similar in size, but compacted to a much smaller region. So these 2 models that were published on day 10 after the earthquake sequence started are still up on the USGS event pages, and will be also available in a publication coming in the next week or 2. So look for that. And finally, I'll leave you with some takeaways. So we can use a combination of regional distance, seismic and geodetic observations to help characterize our rupture process when teleseismic data is poor quality. So in that case, just as a reminder, for the Haiti event, having the local data was important because our teleseismic, despite the fact that this was an earthquake bigger than magnitude 7, which we generally say is big enough to model with teleseismic data, because of that earlier magnitude 6.9 earthquake in Alaska that was sort of contaminating the teleseismic signal, we didn't really do a good job at modeling this unilateral westward rupture until we included regional strong motion accelerometer, static GNSS, and INSAR interferograms. And then next, both the examples of the Petrolia, California earthquake and the sequence in Turkey show us that complex multi-segment ruptures can be clarified if we have access to these local seismic and geodetic data sets. The Petrolia sequence in particular clarified that local data can help to illuminate the complexities of moderate magnitude events that we are not able to observe quite as often. And we were able to understand this sort of complex slip pattern that was partitioned between an offshore and onshore rupture. And then for the Turkey event, this INSAR data in particular was critical for helping us to map the accurate rupture trace. And then we used accelerometer, GNSS, and INSAR observations to help clarify where the slip actually happened and how much. And finally, this is becoming regular practice at the USGS National Earthquake Information Center, so you can expect to see more joint seismic and geodetic slip characterizations from us moving forward. So next time there's an earthquake of interest, please visit earthquake.usgs.gov, click the event you'd like, and then the finite fault tile, like the one you see here, and feel free to send me any comments on how you think our model is and what we can do to update it. So with that, I'll wrap up, and I'm happy to take any questions. So thank you all for your time.
Excellent. Thanks, Dara, so much for that fascinating talk. I just want to remind folks, if you're tuning in live to today's webinar, please, if you have any questions, please go ahead and enter those in the Q&A box. We've already had a couple come in that I will read through. One question I wanted to ask off the bat has to do with the INSAR data, because it looks like, particularly in the case of Turkey, that was really helpful in allowing you to sort of tweak your finite fault model so that it was more in line with the data. I'm curious to know, like, are there plans to more directly incorporate the data you get from INSAR into future finite fault model products versus just kind of using it as like an eyeball guide to see, like, okay, these are the faults we want to include?
Yeah, so thank you for asking, because I think I forgot to mention it in as I was going through it, but we used it both ways. So that we used the INSAR to map the rupture orientation and then kind of oriented our 3 fault segments, but the downsampled INSAR line of sight also went into the inversion. So it used teleseismic data, downsampled INSAR line of sight, GNSS, and strong motion data.
Okay, excellent. We had a question come in from Barry here that says, with respect to the W phase product, is there detailed information available, such as centroid offset times or locations, things like that? And if so, where would one obtain those data?
I don't know if we have that level of detail, but also on here, I can do this faster. If you click on the moment tensor solution and then scroll down, then go to the download section, there is an XML file that has sort of all of the data that goes into producing, or sorry, not all the data, the moment tensor model information. And I'm not sure if that will have the details that you're looking for, but if not, feel free to shoot me an email and I can try to help you figure out where to look.
A question from Bill Harbert here. He asked, with regards to the Turkey earthquake, why was there a 2-day delay in getting strong motion accelerometer data for that sequence? And I think you alluded to some of that it was maybe taking a little while. Is that a typical amount of time, or was it this maybe longer than normal?
So we had access in more or less real time to a sparse data set, the KO network, which is available publicly, but AFOD, which is, from my understanding, sort of the USGS equivalent of Turkey, their data is not publicly available. So we relied on really personal connections that scientists at USGS had with colleagues in Turkey from previous collaborations to get access to that data. And when we did get it, because it was data that we're not used to receiving in real time, it meant that we also had to write some scripts on the fly to get it to reformat so that it worked in our products like ShakeMap. So in other parts of the world, and certainly domestically, we have access to strong motion data in real time. It just was not publicly available in the density that we needed for this event in that time frame.
Thornley wrote in with a question: is there a plan to incorporate modeling and inversion of tsunami observations as well? This has been important for resolving offshore slip, which is not well constrained by onshore GNSS and INSAR data.
Yes. So we have been testing Dart buoy integration into our modeling code. It is not ready for real time yet, but that is something that's on our to-do list. We've been using it to work on some Alaskan earthquakes and do some testing there. So hopefully in the not too distant future, that will be part of our modeling efforts as well.
Speaking of that local strong motion data, there was a question here that wondering if you account for site effects at the strong motion sites as part of the conversion process.
No. So the data is filtered, so we're getting the frequencies that hopefully we can trust, but no, sometimes we end up throwing out stations that clearly have, like, long ringing signals that suggest that there are significant basin effects. So we try to use as much as possible, and then there's sort of some subjective modeler decisions when you look at the data fits to decide if stations with large side effects just can't be used for this purpose.
Do you have any local velocity models that go into these calculations, or is that another area where you kind of just have to take a wag and see how it turns out?
A combination. So we're using what the velocity model that automatically goes into calculating the Green's functions for the local data is from LIF 1.0. So it's maybe not the highest accuracy, and sometimes, but it's great for a rapid model and does better than like a global velocity model for those data sets. So we grab whatever LIF 1.0 is at the location of the hypocenter and use that for our local velocity model. If it's in a region that's been very well documented and there's a velocity model, the published velocity model that we know is better, we can substitute that. But that is definitely a day 2 update, not a first model publication.
We have a question here saying aftershock forecasts based on Coulomb stress changes would be strongly affected by the evolutions in your finite fault modeling. Do you think future efforts could be directed towards obtaining the most robust version of the model in less time? Maybe, yeah, I guess essentially like how can you get your results faster?
Yeah, well, I just want to point out in the context of Coulomb fault modeling, if you go to scroll down on the finite fault tile to the download section, every finite fault model that we post auto generates an input file to Coulomb 3 software. If you use that, so we don't calculate it, but we make it available so other people can use it in their research. The ideal way for getting these models out faster is to transition from what you've been seeing in this talk, which is a teleseismic model that then gets updated with local data, to having real-time access to the local data, which maybe we only need a few minutes of data to see the entire earthquake. And so we can start calculating a finite fault model with 5 minutes of data instead of waiting tens of minutes for teleseismic data. So that's the ultimate goal, and we're working on sort of hardening our processes for getting real-time local data, especially real-time GNSS data. And we've done a bunch of work that shows that real-time GNSS data is sufficient for modeling earthquakes of magnitude of interest. Post-processed data is, of course, higher quality, though, and that's available in the days to weeks afterward. But yes, that is the enormous goal of my work, is to sort of transition us from teleseismic first updates with local data later to local data first update with teleseismic 40 minutes later.
A few final questions here. We had a few of them come in wondering about the use of the models in terms of measuring against slip. So in the case of the events in Turkey, do the finite slip models predict slip at the surface? And how do the finite slip model results fit the ground ruptures mapped by INSAR? So can you use some of the data you're getting from INSAR to estimate the fault offsets? And does that feed into your model, given that your model would have slip at the surface?
Yeah, so it's a little tricky because we used the INSAR line of sight in our model, so it's a little circular to use it and then see how well we predict it. We could take the INSAR out and try it. One of the limitations of our modeling capabilities at the moment is that although we can do multi-segment rupture, we're still relying on planar segments. And so when you have a complicated fault trace and you're including INSAR displacements near the fault, when you're using planar faults, being on like the wrong side of the fault every so often really messes with our ability to fit the INSAR data. We do also include in the finite fault tab download section an estimate of surface displacement, vertical and horizontal surface displacement. And I'd be very curious to see how that, how researchers use that, if anyone uses it, and how they're finding our model fits.
The last question, would it be possible to archive each model output with appropriate versioning so that these can be reviewed by others?
Yes, so we are, for events of interest, we currently we are archiving them sort of ad hoc in a USGS science-based data release. The science-based data release that includes the 4 versions for the Turkey main shock and the 3 versions for the Turkey aftershock is complete and will go live as soon as the accompanying paper is released in the next couple of weeks. So feel free to send me an email and I can send out the link for that, and you can see all 7 of those models archived. And we're hoping in the future to make that sort of an automated process so that future finite fault models that we post can always be automatically archived, rather than this, interesting earthquake by interesting earthquake.